Alright, welcome. In this video we're going to talk about determinants. And up to this point we have heard this word, I think in this class before. We've kind of worked with them on a level of 2 by 2s. Okay, so what we know is that the determinant of a 2 by 2, it's like the kind of a fish looking thing. It's AD minus BC. And that we also have heard that the determinant of a singular matrix is 0. That's a good test. If a determinant of a matrix is 0, that means it's singular, and if it's singular, that means its determinant is 0. And we could say the same thing about non-singular and non-zero. Okay, so and if you want to know like kind of what it means on its own, then watch the 3-1 Brown on it. It's great, right? It will show you what the determinant represents in its own right. But in reality, in linear algebra, at least in my experience, the determinant is more of a tool that we use along the way to some other result. Like, for instance, showing that a matrix is singular or non-singular, or other similar situations. More immediately, we recently solved the eigenvalue problem for 2 by 2 matrices. We saw that it required us to, get a characteristic polynomial that came from a determinant. That's an example of what I'm talking about. A determinant is just a step on our way to finding what we actually want. But if we were interested in finding the eigenvalues for a 3 by 3 or higher, we'd be kind of stuck without knowing how to take the determinant of those type of matrices. So that's where we are. Okay, so technique number 1 is going to be called cofactor expansion. And so that's what's going to start with the fish. Okay, so we're going to start with a 2 by 2. We already know how to do this. And the vertical bars on the outside of the matrix, that means we're taking the determinant. Okay, so we're going to do kind of the fish thing. And we're going to say, okay, well, that determinant is going to be equal to 10 times 6 minus negative 5 times 9. I know you already know this, but just laying it out for you. And that's going to be 60 plus 45 is equal to 105. Right, now when it comes to a 3 by 3, I've got good news for you. You actually already know how to take the determinant of a 3 by 3 if you're in my linear algebra class. I showed it to you on the first day of school. I just didn't tell you that's what it was. Okay, so my message for you, the big reveal, is that all along the cross product has been a determinant. Okay, so this process is going to feel very familiar. Okay, so if we were given this 3 by 3 matrix and said, hey, find the determinant of this, okay, I would ask you to think about the cross product as an analogy. Okay, what if you were crossing negative 1, 4, 5 with 1, 6, 7? You would put an ijk on the top, and you would start off by writing off to the side I minus j plus k. Okay, that's what I trained you to do. But we're going to do the same thing over here. It's just going to be 1 minus 2 plus 3. And then we're going to take the determinant of a submatrix using the fish-looking thing, just like we would have over off to the side if we were taking that cross product, okay, which you do already know how to do. So when I'm starting with the 1, really what I told you to do at the very beginning, which we may have kind of forgotten about, is we kind of block off the corresponding row and column and take this determinant that's left. So it's going to be 28 minus 30 is negative 2. Okay? And then I'm going to do the same thing with 2. So I'm going to block off that column and this row. And I'm going to say, okay, negative 2 times the determinant of what's left. Negative 1 times 7 is negative 7, minus 5 more is negative 12. Okay, and then I will get rid of that. Usually we kind of use a finger to do that. And then plus 3 times, okay, so I'm going to block off that column and that row. And say, okay, negative 6 minus 4 more is negative 10. That's a lot of negativity here. Okay, and now I'm going to add those all together. And I'm going to get, okay, what's that going to be? Ooh, probably should have thought of that ahead of time. Negative 2 plus 24 minus 30. So negative 32 plus 24, that would be negative 8. Okay. Now, I've got another message for you. What we did there where we chose for the top row, that was not special. We didn't necessarily have to choose the top row to anchor our whole computation over. Okay, on this one, I don't really see much of an advantage to any row or column. Maybe you might, in the long run, like column 1, and that's what I'm going to do. I'm going to compute the determinant using column 1 for my cofactor expansion and show you it comes out the same way. So if I used that, I would have 1 minus negative 1 plus 1, okay, and then I'm going to, for the first one, I'm kind of covering up the first row, and that's going to be, again, 28 minus 30 is negative 2, okay, and then I'm going to have minus 1 times, what's that going to be, 14 minus 18 is negative 4, okay, and so I bet the last one's going to come back negative 2. I'm going to get rid of the third row, and I'm going to get 10 minus 12, what do you know, negative 2. And we add that all together, and we get negative 8. Now, had I chosen the middle row or the middle column, the second row or the second column, done all those same computations that you don't need to see me do again, you would get positive 8. Okay, and we know that like the determinant's negative 8. We just computed it 2 different ways and got negative 8. So we should be getting negative 8. And that's the deal. When you go and you do cofactor expansion based on a row or column with an even index, instead of plus minus plus, it's going to be minus plus minus, and that would give you negative 8. Okay, now I do recognize I have not given a definition of the determinant, nor will I be giving a definition of the determinant, because this is a very introductory linear algebra course. Okay, and I actually think that the definition of the determinant actually just makes things much less clear. Okay, so I'm just going to show you how to compute it, what we do with it, we're going to use it, but we might not write down a definition for it, and that'll be all right, because you went through my calculus class and we never really wrote down a definition for a limit. Okay, now 4 by 4. And I'm going to do this one, and you can imagine what 5 by 5 would be like. You know the process, and I think you suspect what the process is going to be right here. We won't need to go higher than that for cofactor expansion. In fact, I would say higher than that. We're going to be using row reduction, the second technique, or just technology, right? And, at the end of the day, technology can do this. It's important that we understand the concept of the computation, but we're not going to do any real crazy ones. So I'm looking for a strategic row or column. I'm seeing that third column. I really like that. 1, 0, 0, 0, or the third row. I really like that one. Maybe you're looking at the second column. Maybe we can do both of them. So this determinant is going to equal 1 times the determinant of, I have to get rid of that row and column, so that would be negative 3, 0, 0, 4, 1, 7, 5, 3, 9. Okay, 1 minus 0 plus 0 minus 0, and these are all going to be multiplied by somebody else's determinant, but these are all zeros, so it doesn't really matter. So I can think about, oh, well, it's going to be the determinant of the submatrix that I'm saying over there. The cofactor matrix is actually what it's called. Okay, well, I'm going to choose that first column, and so that's going to be negative 3 of something plus, minus 0 of something else plus another 0. So negative 3 of times 9 minus 7 times 3, so 9 minus 21. Oh, goodness. Okay, so that's going to be negative 12 times negative 3 is positive 36. So that's my determinant. But maybe I'll try to compute that a second way, maybe using an even indexed column. Okay, so this is going to equal, it's negative, positive, so the negative of negative 3, negative, positive, it doesn't really matter because they're zeros, but it's going to be positive 3 times the determinant of the cofactor matrix where I get rid of that row and the corresponding column. Okay, so like that. So that's where I'm going to get 2, 1, 4, 1, 0, 7, and 3, 0, 9. Okay. And now this is going to be, all right, well, now I need to think about, oh man, that second row looks really nice for me. So I'm going to do that. So that's going to be 3 multiplied by, okay, this is not going to be standard notation here, I don't think, but 3, that's the original, the same 3. In fact, I might actually put a highlighter on that. Oh, the highlighter is really small right now. Okay, so there you go, same 3 there. Okay, multiplied by, okay, I'm using 1 as or I'm using the second row of the cofactor matrix, so -1 plus 0 minus 0. -1 is going to be multiplied by, this is one, it's a little tricky, 9 minus 21. Okay, so 3 times 12, yet again, is going to equal 36. And so that's what we were supposed to see. I'm glad that worked out all right, because I did not work this one out ahead of time. Right, now, second technique is going to be row reduction. And I'm not going to prove these facts for you in general. I'm just going to show you some evidence on a 2x2. And I'm going to tell you it works for higher order ones. And if you wanted to prove that, you could do that on your own. But that's going to be, pretty intensive algebraically to get into, and that's not the point of this video. It's about computation. So we know that this determinant is going to be 20 minus 18, it equals 2. So let's think about what happens if I swapped row or column. Let's do a row swap. Okay, 5, 3 would go on the bottom and 6, 4 would go on the top. And now I've got 18 minus 20 equals -2. Okay, that's interesting. And maybe you already see what's going to happen if I column swap, but I can't see these things quite as quickly as y'all can sometimes. Okay, so 18 minus 20 yet again is -2. So the impact is it makes the determinant negative. Okay, if we were to multiply a row or column by a non-zero constant, well, I guess if we multiplied it by a zero constant, it would still work. Let's just multiply row 1 by 10. Okay, 50, 30, but leave row 2 the same, 6 and 4. Okay, so that's going to be 50 times 4 is 200 minus 180 equals 20. Okay, now we're going to multiply a column by probably a different number, I think would be good. We'll multiply it by -3. How about the one on the right? So 5, -9, 6, -12. Okay, now that'll be -60 plus, wait a second. 6 times 9 is 54. Okay, so -60 plus 54 is -6. Okay, so that would be -3 times the original determinant. Okay. So I might just say, okay, the impact is going to be, we're going to multiply the determinant by that same number. Okay, now if I were to multiply the matrix by a constant, okay, let's say I multiplied it by 5. The whole matrix. So I need to go back and look at it. It's 5, 6, 3, 4, so 25, 30, 15, 20. Just making sure, 4 times 5, 3 times 5, 6 times 5, 5 times 5. Okay, great. Okay, so we're going to look at this, and I think you can see, okay, well, really what I did was I multiplied 2 different rows by 5, so I'm probably going to multiply the determinant by 5 twice based on the previous result, but let's just think about it. 25 times 20, that would be 500, minus 450, that's 50. Okay, and so that is 25 times the original determinant. And so we can say, okay, it'll multiply the determinant of the matrix by that factor to the nth power if A is an n by n matrix, if that's the number of rows and columns that it's got. Okay, now the big one, question 4, what's the impact of adding a multiple of one row to another? So let's just add row 1 plus row 2. So 5, 3, 6, and 4. Okay, I'm going to try to get that. Okay, so I'm going to add them together. So I'd have 5, 3 is the first row. And then 6 and 4, if I'd added that, would be 11 and 7. Okay, I'm taking that determinant. I see what's going to happen. 35 minus 33 is equal to 2. It's like, oh, it didn't change. But maybe that's just because I added one copy of row 1 to row 2. Maybe if I added multiple copies, or if I subtracted. So maybe I will subtract 2 copies of row 1 from row 2. Or maybe row 2 from row 1. So 5 minus 12, 3 minus 8, then leave row 2 unchanged. And that's going to be negative 28 plus 30 equals positive 2. It's like, oh, wow, that is really not changing. Now let's think about adding one multiple of a column to another. That's something we really don't do very often, but we could. Okay, so let's add, or let's subtract 2 of column 2 from column 1. So 5 minus 6 is negative 1. 6 minus 8 is negative 2. 3 and 4. Okay, so that's going to be, all right, negative 4 minus negative 6 is positive 2. And so this one is going to leave our determinant unchanged. And so that means that we can use row reduction, to compute determinants. Does not, oh, but then there's also, I guess there's another fact that you don't know yet that will make that helpful. Does not change determinant. Okay. Okay, that key fact that I need to tell you about is that the determinant of a triangular matrix can be found by multiplying down the main diagonal. Okay, and this is a really useful result for us. Okay, this will be helpful in a variety of ways. And I think we actually saw maybe a little shadow of this last time when we were able to read the eigenvalues of a triangular 2x2 matrix just off the main diagonal. Same idea. Okay, so we can multiply down the main diagonal to find the determinant of a triangular matrix. Let's show some examples of that. Okay, so for example, let's say we've got an upper triangular matrix like that. Okay, I'm going to say that determinant is going to be equal to, I'm going to definitely use that first column, so it's going to be equal to 1 multiplied by the subdeterminant. It's 24 minus 0, okay, minus 0, plus a bunch more zeros. Okay, I think that's the easiest way to explain it, and just think about how, okay, really all we needed, we had used the 1, and then we got rid of that row in that column, and then we took that subdeterminant, which really was only because of that placement of that 0, it was just that, so I multiplied down the main diagonal. Let's do a 4x4, and let's make it lower triangular, right? I'll show you it's no different. Okay, so I'm going to make this one 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can do that. And then we're just going to fill out the rest with zeros. All right, and so I'm going to say, okay, I'm going to choose the most advantageous row or column for me, and that's going to be row 1. So this thing is going to equal 1 multiplied by the determinant of 5, 0, 0, 6, 8, 0, and 7, 9, 0. Which is going to equal, okay, so that's that thing here. I'm going to again use that 5. So that'll be this 5 multiplied by, cross out that row and that column. Wait a second, okay, I didn't write in my 10 there. That makes a lot more sense. 5 times 8, 9, 0, 10. Take that determinant. Well, I guess it was 1 times 5 times this. And so, there we go. So this is all, whoops, equal to 1 times 5 times 8 times 10. And that's going to be 400. And so really, this is true because of cofactor expansion. Okay, now this does give us, kind of like a set of steps for computing a determinant by row reduction. First, what we're going to do is we're going to reduce to echelon form. No need to go all the way to reduced echelon form, because then we'd just be multiplying a lot of rows by a lot of constants, and then we'd have to keep track of even more operations. Okay, then once we get it in echelon form, which is necessarily a triangular matrix, then we're going to multiply down the main diagonal. Okay, so let me show you what I mean by that. So for a quick example, I've got this matrix M here. It's a 4x4. I don't think it would really be that bad to do cofactor expansion on it, but especially if you chose the first column, because then, the second row has all those zeros. But we're trying to use row reduction here. So what I'm going to do is I'm going to start by clearing out the first column. So I'm going to have 2, 0, 0, 0. That's my goal. And I'm going to make this thing upper triangular. So I'm adding row 1 to row 2. So 2 plus 1 is 3. 0 plus 1 is 1. 0 plus 1 is 1. I'm adding row 2 to row 3. So okay, I'm getting that 0. Negative 1 plus 1 is 0. 4 plus 1 is 5, and 0 plus 1 is 1. And then I don't think I'm doing anything to row 4. Okay, and oh, I didn't really do anything to row 1 either. Okay, now I am going to subtract. Wait a second. Yeah, okay, I'm going to subtract 3 copies. I think I made an error here somewhere. But yeah, I'd like to kind of remove the 3, and use the 1, and then just do a row swap later. So, so what I should probably do if I was going to get away with like doing only row operations to get it to triangular, I could just do that and, do all of that. But I should probably say that this determinant is equal to that original determinant. And now I'm going to row swap. I'm just going to do it preemptively to show you what I'm talking about. To track my changes, okay, I just put a negative on the outside. Okay, so 2, 1, 1, 1. I'm swapping row 2 with row 4. 0, 1, 4, 6. 0, 0, 5, 1. And it's looking good. What I'm going to do is subtract 3 copies of what used to be row 4 from what used to be row 2, and then drop that off in row 4. Okay, so that would be 3 minus 3 is 0. 1 minus 12 is negative 11. Yeah, that definitely made an error or something when I was setting this problem up. And then, but it'll be all right. And thinking here, 6 minus 3 is 3. Oh, lovely. Okay. Yeah, don't love this, but I can divide by 5. It's not at the end of the world. So if I divide the row 3 by 5, my new determinant is 1/5 of what it used to be. So the true determinant is 5 times this one. And I know that's a little tricky, but you just got to think through it. Okay, basically, I know what to do. I'm going to switch color. I call the blue matrix. Okay, so I still have that negative from the same negative I had before. And I'm going to have 2, whoops, I'm switching to blue. 2, 1, 1, 1. 0, 1, 4, 6, 0, 0, 1, and 0.2, and then 0, 0, negative 11, and 3. So the determinant of the blue matrix is 1/5 the determinant of the red matrix. Okay, and the red matrix is basically the determinant of the black matrix. So if the blue matrix is the determinant of blue is 1/5 the determinant of red, then the determinant of red is 5 times the determinant of blue. Okay, so I'm going to say that's going to be negative 5 multiplied by that matrix, or the determinant of that matrix. Now I'm going to add 11 of these, so 3 plus 2.2 is going to be 5.2, and I'm going to say, all right, so that's negative 5 times. And that's the thing, is like, a matrix of all integers, its determinant should be all integers, but that dividing by 5 and multiplying by 5, that'll put it back so that you get an integer answer. Okay, so 2, 1, 1, and 3 plus 2.2 is 5.2. All right. And, it might have been better for me to leave that as a improper fraction, honestly. But I'm kind of glad that this one worked out to have decimals in it, because it kind of shows my point, and shows all the different things we might need to keep track of. Okay, I can take the determinant of this new black matrix by just multiplying down the main diagonal. 2 times 1 times 1 times 5.2 would be 10.4. And if I multiply that by negative 5, okay, 5 times 0.4 is 2, that's going to equal negative 52. Okay. And maybe on this one in particular it would be easier to use cofactor expansion, but there's going to be quite a few of them. We're going to prefer to use row reduction. What I will say is, like a calculator, don't use a calculator to row reduce the thing to try to find the determinant. First of all, it's not going to report the steps it took and what it divided and what it row swapped. But second of all, just more generally, in for a penny, in for a pound, if you're going to use technology, just use technology to compute the determinant of the matrix. Okay, you need to know how to compute it without technology though, so that's my recommendation, is that you spend a little time practicing. Okay, so that's going to be all for this video. In this video, I'm just focusing on how to compute it. I'll come back with a separate, very short video on determinant properties. Actually, no, change my mind. No need for that. Okay, this is going to be real quick. So suppose the determinant of matrix A is Q. The determinant of the transpose is the same as the determinant of the original. Okay, I'm not proving that for you here, but it's true. Determinant of A transpose is also Q. The determinant of the inverse of A is going to be 1 over the determinant of A. Okay, and if the A is not invertible, if A inverse doesn't exist, we know that's because A is singular and the determinant is 0, so that would make sense that the determinant would be 1 over 0. It doesn't exist. Okay, the determinant doesn't exist because the inverse doesn't exist. Okay, so the determinant of K times A, well, we would need to know the dimensions of matrix A. So suppose A is n by n. Okay, then the determinant of Ka will be, we'll take the determinant of A and multiply it by K to the nth power. And then the last one, and possibly the most important one, is the determinant of a product. Okay, that is the product of the determinants. That is a fact. And, there's a few determinant property questions on the upcoming homework. Okay, so I think that's going to be all for this video. That's a pretty detailed, pretty long video on determinants and how to compute them. So thanks for watching.